Okay, so we are going to continue our discussion tonight with chapter 15, which is our buffer and titration chapter. So we're just going to go through a slightly updated schedule for SI. So tonight we're supposed to focus on buffers, but titrations take a while. And last time I felt like I was rambling a lot about titrations. And so while we go through the titration stuff tonight, I'm just going to stop a lot and ask if there are any questions. And even if you don't have questions, if you can just provide a little bit of feedback, just say, no, I'm all set at this point in the chat. If a couple people send that, that's fine. I just really, it's a lot harder with everything being on computer screens. It's hard for me to tell if people are getting it or completely lost and don't want to ask me to go through it. But titrations, again, the nice thing about them are the professors don't really throw curveballs. So what I'm showing you for titrations is likely how you'll see it on the exam. And so again, I just really want to take our time tonight going through these titrations, making sure that we completely get them before moving on to buffers, right? So with any remaining time we have tonight, I do have some buffer things to go over, a couple of example problems along with maybe 2 informational slides. If we have to push some of that off, that's completely fine. Again, our biggest priority is to answer any questions relating to titrations. On Wednesday, because this is exam week, we'll be doing a chapter 13 and 14 review. And so again, I'll kind of just go through a content review, answer any questions, and then we'll go, I'll provide some multiple choice challenge problems to help you guys prepare for the exam. Again, your exam on that is Friday. Then kind of looking forward to next week. So next Monday, we'll continue on with our discussions of chapter 15, focusing on whatever is remaining for buffer problems, and then chapter 15 wrap up. So any small points that we haven't touched on yet, or going back, maybe hitting on some things that we're still not as comfortable on, right? So if you guys want to go over a specific type of titration problem, where we're before equivalence point or at the equivalence point, we can really focus on that next Monday. Then, you can kind of look at that after next Monday. We'll move on to chapter 16 and then do a review before all the way in April. You have an exam on chapters 15 and 16. Okay. And so that's kind of the SI schedule for the next 3 weeks. I know it's kind of forward thinking, but really what I wanted to emphasize is that there's plenty of days to go over chapter 15. And so again, I really want us to take our time and make sure it makes sense to everyone. Okay, so I gave 2 challenge problems at the end of last Wednesday's session. They were both titration questions. The first one, which is the one we're looking at now, is a strong acid being titrated by a strong base, or I guess here technically we have a strong base being titrated by a strong acid, but it's a strong titration. And then the second problem, we start with a weak base that's titrated by a strong acid. Okay, so in this problem, we're going to have a fixed volume and concentration of calcium hydroxide, and we're going to be titrating it with different amounts of 0.6 molar hydrobromic acid. Okay, so while reading this problem, when you see calcium hydroxide and hydrobromic acid, it's really important that you recognize that these are both strong acids and bases respectively. Okay, so remember that strong bases typically have hydroxide as a group in them, while strong acids, there's 6 of them that you need to know. They are hydrochloric acid, hydrobromic acid, hydroiodic acids, right? So those are kind of your halogens minus fluorine. And then your other 3 strong acids are sulfuric acid, nitric acid, and perchloric acid. Okay, so you should recognize those 6 as strong acids, which means they dissociate completely. Okay, so let's look at how we actually solve this problem. Now, as I stated, the volume and concentration of calcium hydroxide remains constant throughout this entire problem, right? In part A, B, and C, we're still going to have the same volume and concentration of hydroxide. And so at the top, before I even start the problem, I find how many moles of hydroxide we have, right? Remember that in titration problems, we're always going to plug moles in to our ICE table originally, right? We have to compare moles. So from our calcium hydroxide, we have 0.06 moles of hydroxide. Now, before I actually go through the rest of the problem, I'm going to look at each individual part and see how many moles of H plus or protons I'm going to get from my hydrobromic acid, right? So in part A, we're going to add 75 milliliters of 0.6 molar HBr, part B, 100 milliliters, and part C, 105 milliliters. And so I basically do the same exact calculation that I did above for calcium hydroxide. I'm just doing it for HBr to find how many moles of H plus I have, right? Remember, H plus and HBr would be in a 1-to-1 ratio because HBr is a monoprotic acid, meaning it has one proton. So in part A, I find that I'm going to add 0.045 moles of H plus. Okay, in part B, I'm going to be adding 0.06 moles of H plus, and in C, I'm adding 0.063 moles of H plus. Okay, so in part A, when comparing my moles of H plus to moles of hydroxide, right, I can pretty quickly see that I'm going to have excess moles of hydroxide. Okay, in part B, I can see that I actually have equal amounts of H plus and hydroxide. And then in part C, I'm actually going to have excess H plus compared to hydroxide. Okay, so whenever you're doing a strong acid, strong base titration problem like this, right, you're going to solve it in one of two ways. The first way, you're going to use anytime you have excess hydroxide or excess protons, right? So the first method we're going to use for part A and part C. The second method we're going to use for B. Okay, so coming to part A, right, whenever we do a problem where we have excess H plus or excess hydroxide for a strong acid, strong base titration, we're always going to start out with our net ionic equation, which for, again, strong acid, strong base will always be H plus hydroxide goes to water. Okay, and we're going to make an ice table, and we should have an initial amount of H plus and hydroxide, right? My initial amount of H plus is going to come from my HBr, so it's 0.045 moles, and my amount of hydroxide is going to come from my calcium hydroxide, so 0.06 moles. Okay, and a key to this is that these are going to combine to make as much water as they physically can. Okay, so basically, you're going to make water until you run out of H plus or hydroxide. Okay, so the change here is going to be negative 0.045 moles, right? Because we're going to use up all of our H plus to make water. Okay, so for our change for both reactants, it should be minus 0.045, meaning at equilibrium, we have 0 excess H plus, but we have 0.015 moles of excess hydroxide. Once you find how much excess hydroxide you have here, right, you're going to take that and you're going to divide it by your total volume to find your molarity, right? So our total volume here is 0.15 liters, which is 150 milliliters, which is how much base we had, right, calcium hydroxide, plus 0.075 liters, which is 75 milliliters, which is how much acid we added in part A of this problem. And so when we add together to find the total volume, it comes out to 0.225 liters. And when we do this division, we find that the molarity of hydroxide is 0.067 molar. Now that we've found our concentration of hydroxide, right, we can plug it in to find our pOH. So our pOH is equal to the negative log of our hydroxide concentration. And so when I plug in this value of hydroxide, it comes out to 1.17 as a pOH. And so I can quickly find my pH because pH plus pOH must always equal 14. Okay, and so I use my value of pOH, which is 1.17, to find that my pH is 12.83. Okay, and so again, this is how we solve part A when we have excess hydroxide. We're going to solve for part C in a very similar way. Okay, but first we'll quickly look at part B. Now, part B, people often love because in a strong acid, strong base titration, whenever your moles of H plus equals your moles of hydroxide added, whenever you just find that those are equal, you automatically know your pH is 7. Okay, so for part B, you actually don't need to do any work. As soon as you find that you have 0.06 moles of H plus and 0.06 moles of hydroxide, right? If you have equal numbers of each, for a strong acid, strong base titration, the pH will always be 7. Okay, if you have a weak acid or base in the problem being titrated by a strong acid or base, your pH at equivalence point won't be 7. Okay, so this only works for a strong acid, strong base titration. Okay, but again, when the moles of H plus equal moles of hydroxide, for this type of titration, you don't need to do any work. pH equals 7 right away. Okay, and so now let's look at part C. Now remember, we're going to solve part C just like we solved part A. This time, we just have extra H plus instead of hydroxide. Okay, and so I'm going to write my ice table again. I'm going to write my net ionic equation at the top. So H plus hydroxide goes to water. I plug in my initial amounts of H plus and hydroxide. So I have 0.063 moles of H plus, 0.06 moles of hydroxide. I'm going to form as much water as I physically can, right? So my change is going to basically be whichever initial amount is lower, right? So my change is going to be negative 0.06 for both of these so that I use up all of my hydroxide, right? At equilibrium, I'm going to have 0 hydroxide, and I'm going to have 0.003 moles of excess H plus, right? It's excess H plus. Okay, and so once we find how many moles of excess H plus we have, we're going to divide it by the total volume. So the total volume in this problem is 0.15 liters, which is from calcium hydroxide. It's 150 milliliters, plus 0.105 liters of acid, right? We added 105 milliliters of acid in this problem. Okay, so our total volume in this circumstance is 0.255, and I can find that my molarity of H plus is 0.01176 molar. And so here I can find my pH by plugging my H plus concentration into the equation. So pH equals negative log of my H plus concentration. pH is 1.93 in this circumstance. Okay, and so the one thing that I kind of caution you to, or tell you to be wary of, is realize that when we do the molarity calculations, so moles of excess H plus or moles of excess hydroxide, if it's part A, when we divide it by the total volume, just realize that the total volume number will change depending on what part of the problem we're on, right? So if we go back in part A, we would have 150 milliliters of base plus 75 milliliters of acid. In part B, we'd have 150 milliliters of base plus 100 milliliters of acid. Part C, 150 milliliters of base, 105 milliliters of acid. Okay, so just remember that depending on the part of the problem you're on, this volume, when you're trying to find molarity, it will change. Okay, are there any questions on strong acid, strong base titration questions? Any questions? Awesome. Thank you, people, for the feedback. Again, I just want to make sure everyone is good before moving on. Okay, so question 2 is a very classic weak base titrated by a strong acid problem. Okay, and so this is typically the one that they will ask about on an exam because it is much harder than your strong acid, strong base titrations. Okay, so here we're considering the titration of 200 milliliters of 0.5 molar ethylamine. Okay, now you might not be familiar with ethylamine. I don't really expect you guys to really know that compound. You would kind of learn about it based on the naming of it in organic chemistry, but they give you a KB here, right? So that should indicate to you that this is probably a weak base, right? I know your professors can give you the wrong one, but the fact that it's a KB on a titration problem, again, indicates that this is going to be a weak base. It further says that this is titrated with 0.2 molar HCl, right? HCl is a strong acid. So remember, our two parts of in a titration need to be opposites, right? So because we're titrating with HCl, that again further confirms that ethylamine is some weak base, right? You don't need to know the formula for it, just understanding, okay, this is a basic species. And so we want to calculate the pH at when the following volumes of HCl are added. Okay, and so in this circumstance, the volume and concentration of ethylamine won't change. And so what I do is I use those values to solve for how many moles of ethylamine or weak base do I have. And so when I do that calculation, I find that we will have 0.1 moles of weak base. Okay, and so now I'm going to look at each portion of this problem, A through D, and determine kind of what scenario we are in. Okay, because remember, when we're doing a weak base, strong acid titration, we're going to have 3 different scenarios that we solve very differently. And so I'd say that your first step whenever doing a titration problem, and I think it's probably one of the most important steps, is identifying which scenario you are in. Okay, and so what I do is I take, for A through D, the volumes of HCl solution, and I multiply it by its molarity and solve for how many moles of just H plus am I adding, right? HCl is a strong acid, and so we assume it completely dissociates into H plus and Cl minus. Okay, but we don't care about the Cl minus, it's a spectator ion. And so in part A, we're going to be adding 0.05 moles of H plus, and in B, we're adding 0.09 moles of H plus. So realize in these two circumstances that the moles of H plus added are less than moles of weak base we start with. Okay, and so whenever you're in this circumstance where the H plus that you're adding from the strong species, you have less moles of that than the moles of weak base, you're in the scenario that I call before equivalence point, right? It just means you haven't reached that equivalence point yet. In part C, I find that we add 0.10 moles of H plus. And so here we can see we have equal moles of H plus and weak base, meaning part C, we are at equivalence, which is our second scenario. And then lastly, part D, we find that we add 0.15 moles of H plus. And so here we actually added too much H plus, or too much of this strong acid. There's more moles of that than our weak base. And so this is the third circumstance, or this third scenario that I call past the equivalence point. Okay, and so again, it's important to identify which scenario you're in, because you're going to solve all 3 of these differently. Okay, but A and B, because they're both before the equivalence point, we're actually going to solve those the same way. Okay, so let's look at A. So first I'm going to write my net ionic equation. So I don't know the formula for ethylamine, but I know it's a weak base. So I'm going to denote it by B minus, which again just stands for weak base. And I personally always react on my reactant side, my weak acid or base with water. So I'm going to react my weak base with water to produce my conjugate acid, HB, and hydroxide. And I'm going to write an ice table, and the only initial amount that I have is my initial amount of weak base, B minus, which is 0.1 moles, right? That'll be the initial amount of weak base in each part of this problem. Now my change, you'll notice I wrote negative 0.05 for B minus and plus 0.05 on my product side. Now remember that the whole idea behind a titration is that your equilibrium is going to shift to neutralize all of the acid being added, right? So we're adding 0.05 moles of H plus. To neutralize that, we want to create 0.05 moles of hydroxide, because when they react, they'll form water. Okay, and so that's how I know that my change should be 0.05 and that it should be positive for my products. It's because hydroxide's a product and we need 0.05 moles of it in order to neutralize all of the H plus that we add in scenario A. Okay, so that's how I know my change. And so at equilibrium, I actually only care about how much of my base and conjugate acid I have. And so I find at equilibrium, I have 0.05 moles of each. Okay, if you ever find that your weak base and conjugate acid have the same number of moles at equilibrium, like they do here, you're in a special circumstance called half equivalence. Okay, and the special thing about half equivalence is that when you plug these values into the Henderson-Hasselbalch equation, which is this equation here, right? When you plug in B minus and HB here, when you do that division, it comes out to 1, and log of 1 is equal to 0. Okay, so at half equivalence, your pH will always be equal to your pKa. Okay, that's just a special thing about half equivalence, which this correlates to, or is. And so even if you didn't know that you were at half equivalence, again, a lot of times whenever you're before the equivalence point, which part A is, we're going to use the Henderson-Hasselbalch equation. So looking at this equation, we can tell that we need the pKa. Well, we can find the pKa by using the Ka. So I'm going to first solve for my Ka. So remember that Ka times Kb will always equal 1 times 10 to the negative 14th. So using the value of Kb given in the problem, I can solve for my Ka, which comes out to 1.786 times 10 to the negative 11th. I can find my pKa by taking the negative log of this Ka value. And so when I do that, I find that the pKa in this problem comes out to 10.75. Okay, and so knowing I'm at half equivalence, I can automatically know that if my pKa is 10.75, that's what my pH is going to be. But if you weren't familiar with that kind of unique characteristic at half equivalence point, right, you can still plug in your pKa and your concentration of base and weak acid into the Henderson-Hasselbalch equation, and you would still get that it's 10.75. Okay, and again, that's just because the log of 1 is equal to 0, which will occur anytime our equilibrium concentration of B minus and HB are the same. Okay, I'm going to go on to part B, which is also before the equivalence point, so it's going to use the same process, but then I'll answer any questions that arise on part A or B. Okay, so if anything comes up, feel free to put it in the chat, and I'll get to it in just a moment. Okay, so looking at part B, so again, I'm going to just start out with my same equation written at the top, and again, I'm going to write an ICE table with my initial amount of B minus being 0.1 moles. Okay, that part won't change. Now for the change portion, right, again, remember that the whole idea behind the titration is that this equilibrium will shift to form hydroxide in order to neutralize all the H plus added. So in part B, we found out that 0.09 moles of H plus are being added, which means for the change, we need plus 0.09 moles for hydroxide in order to neutralize it all. Okay, so I'm going to add that amount to the products, subtract it from the reactants, and now I have different equilibrium concentrations of my weak base, ethylamine, and my conjugate acid. 0.01 moles for B minus, 0.09 moles for HB. Again, I can plug this straight into my Henderson-Hasselbalch equation. So I don't need to solve for the pKa again because that won't change in a given problem because Ka is constant for a given acid or base. And so my pKa is still going to be 10.75, and I just plug in plus the log of my concentration of B minus, 0.01, divided by my concentration of HB, 0.09. And sorry, I said concentration, but you can use concentration or moles interchangeably in titration problems in the Henderson-Hasselbalch equation. Okay, and so when I plug all of this in, my pH comes out to 9.8. Okay, so any questions on scenarios correlating to before the equivalence point? Right, basically you're going to put your initial amount of weak acid or weak base. Your change is going to reflect how much strong acid or base you added, right? So I added 0.09 moles of H plus, and so I needed to add equal amounts of hydroxide to counteract that. And then you use your equilibrium amounts of acid and conjugate base in the Henderson-Hasselbalch equation to find the pH. Okay. Okay, if no one's adding anything, I'll probably move on to the next portion. Just as you know, titration questions are great as a self-check mechanism, right? Remember that from part A to part B to part C to part D, we're adding more and more strong acid, right? HBr or HCl. I don't even remember what the strong acid was in this problem. But that means that as we continue on this problem, our pH should decrease and decrease and decrease because we're adding more and more acid. So our pH in part 1 was about 10.75. In part B, it's 9.8, right? Our pH decreased, which made sense because we're adding more and more acid. Okay, so if you ever find that it doesn't follow that trend, that kind of trend of logic, definitely go back. You probably just typed something in wrong or wrote a number incorrectly. Okay, now part C, we're adding 0.1 moles of H plus, which means we are at the equivalence point because we have equal moles of H plus and our weak base. Now this is definitely our most complex scenario. And so what we're going to do is we're going to write our initial ice table and do our change just like we did before, right? If we're adding 0.1 moles of H plus, we want to add 0.1 moles of hydroxide. So again, plus 0.1 to the products, minus 0.1 to the reactants. And so what we find is that at equilibrium, we have no ethylamine or no weak base, but we do have 0.1 moles of conjugate acid, okay? Now, all the H plus has been neutralized by this hydroxide, so there's no more driving force towards the product side. Okay, and so what's gonna happen is our weak acid here is going to react with water and actually shift leftwards to produce our conjugate base. Okay, so to represent this, we make what I call a reverse ice table. Okay, so we're gonna now write on the reactant side that weak acid that was just on our product side. We're gonna put that on our reactant side, react it with water to produce the conjugate base and hydronium. Our initial amount of this weak acid is 0.1 molar, right? That was the equilibrium amount of it from our previous ice table. And then for our change section or our change row, right, we're not sure how much it shifts. So we're just going to put that in terms of X, just like we did in chapter 14. So minus X for reactants, plus X for products, and we're going to write our equilibrium amounts in terms of X. Okay, so looking at this reverse ice table, I'm starting with an acid, right? HB is a weak acid. And so to solve for X, I'm going to need to use my Ka, right? My acid dissociation constant. Okay, and remember that whenever we do Ka, our equilibrium amounts need to be in terms of molarity or in terms of concentration. So we have to convert 0.1 moles minus X for HB. We have to convert that to molarity. Okay, and so what I do is I take my 0.1 moles of HB and I divide it by my total volume associated with part C of this problem, right? Which would be 0.2 liters for my base plus 0.5 liters for my acid. What I find is that my molarity is 0.143 molar HB. And so all I do at the bottom here is I rewrite my equation and I rewrite my equilibrium concentrations or my equilibrium amounts, but this time I put it in terms of molar, right? So 0.143 molar minus X, instead of having it like above in terms of moles. Now that I have my equilibrium amounts in terms of concentration, I can relate them to the Ka. Now in part A, in order to solve for the pKa, we had found the Ka. Okay, so just taking that number that we solved for in part A, our Ka is 1.786 times 10 to the negative 11th, which is equal to our equilibrium concentration of products, which was x times x, or x squared, divided by my equilibrium concentration of reactant, which is my weak acid. I'm going to use the 5% rule to ignore x and find that x, or to ignore x in the denominator, and then I solve for x, which comes out to 1.6 times 10 to the negative 6th. When I do the check for the 5% rule, it comes much less than even 1%, and so that was a valid assumption to ignore x above. Because x equals 1.6 times 10 to the negative 6th, and on the previous slide, we said x is the equilibrium concentration of hydronium, we know that hydronium's concentration at equilibrium is that value. And so we can quickly find the pH by plugging in that concentration. So pH equals negative log hydronium concentration, and our pH comes out to 5.8. Okay. Are there any questions? Sorry, before moving on to part D, are there any questions about how to solve at the equivalence point, right? So C is at the equivalence point, and it is the most complex of them. You do need to do that reverse ice table. Does everybody feel okay with those calculations and the rationale behind why you have to do a reverse ice table? Because the rationale behind it kind of makes the next part make more sense, which is when you have gone past the equivalence point. I'm not quite sure your question. So does the Henderson-Hasselbalch equation only apply before equal? So I think you maybe mean equivalence point. So Henderson-Hasselbalch equation we used it in part A and part B, which was before equivalence point. So that part would be true. You don't use it before equilibrium. Okay, yes. So for titration questions, you don't have to use it. However, I think using the Henderson-Hasselbalch equation whenever you're before the equivalence point is by far the easiest method to solve for your pH. Okay, so I would always suggest that, but yes, before the equivalence point, I would say always use the Henderson-Hasselbalch. Because once you figure out your moles at equivalence, you just plug it into that equation and it's very, very simple and easy. Okay, so moving on to part D. So remember, in this circumstance, we're adding too much H plus, or our strong acid, right? We have more moles of that than moles of weak base. Okay, so the logic is pretty similar in this circumstance, but the issue is that we run out of moles of weak base. Right, so I write my equation, and again, my initial amount of weak base didn't change in any of these parts. We always start with 0.1 moles. Now, I believe we added 0.15 moles of H plus in this problem, which means we want to make 0.15 moles of hydroxide. However, we can physically only make 0.1 moles of product because anything after that, we've run out of reactant. Okay, so we're going to use up all of our weak base and turn it all into product, right? So we're going to have 0.1 moles of HB and 0.1 moles of hydroxide and be left with 0 moles of our original weak base. Okay, now the fact that we still have H plus to neutralize causes this reaction to still favor the formation of products. Okay, so because there's still H plus that we want to neutralize by making hydroxide, which is a product, that's the reason we don't see a reverse ice table really in part D. Okay, also if you did it, it would be a pretty insignificant value. And I think Dr. P went over that in his 3rd lecture video last week. Okay, but basically, if you ever add too much of your strong species, in this case, we added too much strong acid, right? You're gonna make as much hydroxide as you can. And then from here, you're gonna solve for excess H plus or excess hydroxide, right? So because we're adding strong acid and we have excess H plus, we're gonna solve for how much excess H plus we have. So we're gonna do the 0.15 moles of H plus that we added in part D. We're gonna subtract the 0.1 moles of hydroxide that we have at equilibrium. And this tells us that we have 0.05 moles of H plus remaining. Now that we know that, we're going to divide it by the total volume in order to find our molarity of H plus, right? So our total volume here is 200 milliliters or 0.2 liters plus 750 milliliters or 0.75 liters. And so what we find through this calculation is that the concentration of H plus is 0.053 molar. Again, we use that value to solve for the pH and find that the pH is about 1.28. Okay, so that's fully going through both types of titrations that we see in this chapter. Are there any questions before we move on to a few little notes to finish up titrations and then buffers? Just a moment. And actually, I guess this would be a good time to, if you don't have questions, to sign in using your NetID into the chat. And so, yeah, hopefully, if if you don't have questions, that'll also indicate to me that you guys are ready to move on. Okay, I think that's just about everyone. And so we will, again, we're just going to hit on a couple little points of titrations that we didn't have time for last week, and also some things that I kind of found while, again, reviewing the lecture videos today. Okay, so again, kind of just reviewing the titration setup, right? So you'll have a titrant or an analate in kind of a beaker. Knowing these names aren't really important, but right, we'd have a beaker. This beaker is, if we had a weak acid or base, that would be in the beaker portion. Okay, so if we do have a weak acid or base, it'll be in the beaker portion. If it's a strong titration, then one of the strong species would be in the beaker. Okay, but then we have the burette up here with the titrant, and this, the compound in the burette should always be a strong acid or base in this course, right? And so this is the compound that changes in volume, right? From part A to B to C to D, right? We have changing volume because we control how much is added when it's in the burette. Okay, so just a general setup. Again, in this course, we'll see strong titrations, which is like problem 1, and strong weak titrations, right? So as examples in SI last Wednesday, we started with a weak acid and titrated with a strong base. Then during the challenge problems today, we went over when you have a weak base and titrate it with a strong acid. So they're very, very similar, but you've now in SI alone seen each of those. Okay, kind of something I didn't really talk about last time, really just a last note that I want you guys to have is indicators, right? Your professors talked about this a little bit. And so indicators will change color to indicate or tell us when the equivalence point is reached, right? So equivalence point is when the moles of H plus are equal to the moles of hydroxide. Okay, I would definitely note that indicators are often weak acids. Okay, and so I think they even wrote in your slides that you can write it as HIN, for H being the proton, IN for indicator. And so when it dissociates into its ions, that's when you get like a color change. I'm just saying that it's a weak acid. I like writing it as HA better. And then just kind of know the terminology endpoint. That's just when, it's the point when the indicator changes color, right? So different indicators will change color at different pHs, right? So different endpoints. Okay, So really the last thing I want to talk about in relation to titration questions is writing net ionic equations. And if you watched or attended SI last Wednesday, you may have heard that you can write these titration equations in one of two ways. Okay, and if you ever look at the work that I do normally, if I start with a weak acid or a weak base, on the reactant side, I will always react that with water. Okay, that's how I write my equations, just because I like to remain consistent. Okay, so in a titration problem, again, if you look at any of the work we just went through, I took my weak base and reacted it with water to produce whatever's on the product end. Now, by using the net ionic equations, we can write the equations in a different way, but we can get the same answer. And I just really want you guys to know this in case you prefer to write it in the other way. Okay, if you prefer to write it how I write it, where you always react with water on the reactant side, I definitely encourage you to keep using that, but just kind of be aware of this. Also, in case on a multiple choice exam they ever ask you to write the net ionic equation, you can kind of understand it through what we're about to go through. Okay, so this first example is the net ionic equation for a strong acid and a strong base. Okay, and so what happens if we have nitric acid, we react it with potassium hydroxide, so strong acid, strong base. They're gonna form water, right? The net ionic for acid-base reaction should always produce water, plus potassium nitrate aqueous. Okay, so on the product side, we have potassium nitrate, which is a salt, right? It has a metal, potassium, and a non-metal, which is an anion here, and it's the nitrate anion. Now, whenever you have a salt in the aqueous state, right, it actually completely dissociates into its ions, which I show below is K plus aqueous and nitrate aqueous. Okay, now turning our attention to the reactant side, right, we have a strong acid and a strong base. Now, by definition, we say that strong acids completely dissociate, meaning every single nitric acid molecule will split into H plus aqueous and NO3 minus aqueous. And every molecule of KOH will split into K plus aqueous and OH minus aqueous. Okay, so once we kind of split up all of these ions, right, remember to make the net ionic equation, we cancel out anything that appears the same on both sides of the equation. So in this circumstance, potassium and the nitrate ion they both have charges, and they're both in the aqueous state on the reactant and product side. Okay, and so I cross those out, and what am I left with for my net ionic? H plus aqueous plus hydroxide aqueous goes to liquid water. Okay, and so whenever you have a strong acid, strong base reaction, your net ionic will always be this, H plus plus hydroxide goes to water. And for the same reasons we just did above. Okay, but it gets a little more complicated to write the net ionic when you have a weak acid or base involved. Okay, so for our first example, we're going to react hydrofluoric acid, a weak acid, with strong base potassium hydroxide. Okay, so again, I'm going to react these, and I'm always going to form water in these reactions. Okay, so I'm forming water, and what's left? KF aqueous. Now again, KF is a salt, so it's going to completely split up into K plus and F minus aqueous. Turning our attention to the reactant side, now KOH is a strong base, meaning every single molecule will split up into K plus and OH minus aqueous. So that's how I write it. Now you might notice that HF I wrote as just HF aqueous. I didn't write it as ions. And the reason for this is that because HF is a weak acid and not all of it dissociates, we have to keep it together as HF, right? Because at equilibrium, we will have some molecules that have not dissociated into their ions. Okay, and so I'm going to leave HF on that side as I do. And then again, to get my net ionic equation, I'm going to cross out anything that appears the same on both sides. Okay, and so here I'm just going to cancel out K plus from both sides. And so what I find my net ionic equation is for a weak acid strong base, or this titration in particular, or reaction, it'll be hydrofluoric acid plus hydroxide will form water plus F minus aqueous. Okay, and so if you wanted to use this equation instead, you would get the correct answer. And I'll show you that on the next couple slides. Now, what happens if you have a strong acid and a weak base? So for this, we're going to use HCl and ammonia, NH3, to show this. Okay, so again, these are going to react. And this time, we're actually not going to form water. It's kind of a weird circumstance where it doesn't form water when you have strong acid, weak base. But we're going to produce ammonium, NH4 plus, and Cl minus, which because of their opposite charges, they'll make a salt here, right? So these have an ionic bond between them. Now, just as before, we're going to separate anything that completely ionizes, right? So this is a salt, ammonium chloride, and so it's going to split up completely into NH4 plus aqueous and Cl minus aqueous. Focusing on the reactant side, right? NH3, well, NH3 is kind of just, it's a base. It's going to accept an H plus. So that's just going to remain exactly how it was. It doesn't dissociate. While HCl, which is a strong acid, will completely dissociate into H plus and Cl minus. Now looking at this equation, again, I'm going to cross out anything that appears the same on both sides. So I'm going to cross out Cl minus. And so I'd find that my net ionic for this problem would be H plus NH3 aqueous goes to NH4 plus, right? And so I guess I kind of said earlier that it will always form water. I guess that's not completely always true. This is a type of reaction that doesn't occur. But hopefully at least the process of writing the net ionic equation does make sense in case you see it on the multiple choice. If you'd like to use this formula for your titration problems, you can. But if you like how I typically do it, that is also completely fine. You will get the same answer either way. Okay. Any questions before I quickly show you how you can apply these equations to a titration problem, and then just going over the basics of buffers? Okay. If there are questions, I'm happy to come back. Just because of time, I'm going to kind of jump into this. Okay, so this example is one we did last Wednesday. Okay, so we're not actually going to do this. I'm just going to show the work that we went through last SI, right? So we had a weak acid here, barbituric acid, that we are titrating with strong base potassium hydroxide at various points. So in this circumstance, we're going to look at circumstance B, 30 milliliters of KOH added, and D, 50 milliliters of KOH added. Okay, and so in part B, right, we are adding, if you do the math out, we're adding 0.003 moles of hydroxide, and we started with 0.004 moles of acid. Okay, and so what we did is we plugged in our initial amount of acid, we did our change based on how much hydroxide we added, and then we used our equilibrium amounts of weak acid, HA, and conjugate base, A minus, right? We found those equilibrium amounts, and we plugged them into the Henderson-Hasselbalch equation to find our pH. Okay, before I go on this next slide, I just encourage you to kind of pay attention to our equilibrium amounts of HA and A minus. Okay, and I also kind of understand our logic through during the change portion that we add 0.003 moles of hydronium, H3O plus, in order to neutralize all the hydroxide added. Okay, now if you wrote the net ionic equation for a weak acid and a strong base, right, this would be our net ionic equation. Right? Before we did it, HF was our weak acid, right? So this would correspond to HF, A minus would correspond to F minus. Okay, so here again, I'm gonna plug in my initial amount of HA, and I kind of add 0.003 moles of hydroxide, right? By adding that strong base KOH, I'm adding that much hydroxide. Now, remember that the whole point of this change portion is to, and I'm going to go back to the last slide, right? We wanted to add this much hydronium in order to get rid of or neutralize all of that hydroxide. Now, writing the equation in this way, we don't have hydronium, okay? But the goal is still the same. We still want to get rid of all of this hydroxide. And so because I want to get rid of all of that, I know that I need to subtract 0.003 moles from my reactant side and add it to my product side. Okay, and then at equilibrium, if you look, we actually have the same amount of HA and the same amount of A minus. Okay, and so when we plug it into the Henderson-Hasselbalch equation, we're gonna get the same pH. Okay, all this is trying to show is that if you'd rather write it in this way, which is the net ionic equation method, that is fine. Just realize if you're adding hydroxide and your hydroxide's in the equation, your change is going to be trying to get rid of all of that hydroxide, if that's possible to do so. Okay. And let's just show the same thing for part D. Okay, so in part D of that problem I showed, right, we're adding 0.005 moles of hydroxide. Okay, so in our ice table, we're going to make as much hydronium as we physically can. So we're going to make 0.004 moles, right? So we have 0 weak acid to begin with. Again, we have these equilibrium amounts of products. And so here we're going to solve for excess hydroxide, right? So 0.005 moles of hydroxide minus 0.004 moles of hydronium. And so we have 0.001 moles of excess hydroxide. We solve for the molarity of it, plug it in to find POH, and then plug it to find pH. Okay, again, sorry, I'm going a little quickly. If you want me to go back, I'm happy to explain it further, but we did go over this last Wednesday. Okay, so again, we can solve for this using the net ionic equation instead, right? So we have 0.004 moles of our weak acid to start with. Because of the amount of KOH we added, we have 0.005 moles of hydroxide that we want to neutralize by shifting to the product side. And again, these will react to form water and our conjugate base. Okay, and so again, our goal for the change section is to eliminate all the hydroxide. Okay, but in this case, we can only subtract 0.004 moles, because after that, you have no more weak acid that can be converted into products. So at equilibrium here, we find actually how much excess hydroxide we have. So knowing how much excess hydroxide we have, 0.001 moles, we plug it in to find the molarity of it. We can use that to find POH and the pH. Okay, and again, all I want to show is that different equation that represents the same exact titration and both give you the same answer. Okay. Are there any questions on that? Again, I just have about 2 slides for buffers that I want to go over, and then we'll probably go through one example problem because buffered questions are a lot quicker than titrations. Okay, but does everyone have any remaining questions at all on titrations, or do you feel relatively good and confident about those problems? Okay, got it. All good or so. Awesome. So again, hopefully those do make sense. If they don't, feel free to reach out. Okay, so let's talk about buffers. Okay, so buffers are solutions that resist the addition of acid, or H+, and base, OH-. Okay, so it's really important that you realize that it actually resists the addition of both. It's not like it will only resist the addition of acid or only resist the addition of base. Okay, but there is a pretty big requirement to this, and maybe it was Dr. S last week. I can't remember who taught lecture last week. I think Dr. S though talked about in his first or second video the requirements of making a buffer and identifying what is a buffer versus not a buffer. So definitely check out those examples if you haven't. But the key requirement to a buffer system is that it has to contain both a weak acid and its conjugate. Okay, and so you need a weak acid and a weak base, basically. Okay, and so often your weak acid will just be in the form of an acid, and your weak base will usually be added in the form of a salt, right? And so if our buffer solution is between HF, hydrofluoric acid, and its conjugate base, F minus, which is fluorine, the weak base, which is fluorine, would probably be delivered as a salt, KF. Okay, but realize here that we don't actually care about the potassium because only the fluorine is the conjugate of our weak acid, HF. Okay, another thing that I think, again, Dr. S went over last week in lecture is that you can also prepare a solution by partially neutralizing a weak acid or base with a strong base or acid. Okay, so basically you do part of a titration and then, part of the way of neutralizing that, you will have a buffer system. Okay, so that was another thing. That's typically a less common way that you see buffer questions. Honestly, in the past, they haven't really ever taught that. The main method that they've used in past years to indicate that something is a buffer is you'll start with a weak acid and you'll add the salt of your conjugate base. Okay, almost always. Okay, some key points. So again, in buffer systems, a really key thing is that we're seeing neutralization. Okay, and so oftentimes we want our H plus and hydroxide to be the same, right? Especially in that change portion of ice tables, right? If we add a bunch of H plus, we're going to shift our equilibrium in order to have enough hydroxide or OH minus to neutralize the H plus added. Okay, that's just a really key portion, not just the titration problems we just did, but also these buffer questions. Okay, and these little 2 bullet points probably won't make the most sense until we go over the example. Okay, but it says if added acid base, right? So if you add an acid or base portion and that portion is in the equation, your change will be negative X for that portion. Okay, and this is just kind of a general rule. Again, it's going to make a lot more sense, hopefully, when you actually look at the example. I had a really hard time verbalizing this. Okay, and if you're in the scenario where you add an acid or base and that portion is not in the equation, then you'll see plus X. Okay, and again, we'll come to that in just a moment. And in this circumstance, in buffers, our acid and our conjugate base are in the same solutions. And so when you use the Henderson-Hasselbalch equation, you can plug in concentrations of acid and conjugate base, or you can plug in moles, right? You can do them completely interchangeably because their volume will always be the same in a buffer problem, right? Because they're in the same solution. Okay, so just to remind you of the Henderson-Hasselbalch equation, however, we've been staring at it for quite a bit tonight. Hopefully you're getting pretty familiar with that equation and using it. Okay, and then just to talk about the effectiveness of a buffer, this is definitely something I would be very, very aware of. Especially they love these types of questions on multiple choice. Actually, I don't think you get tested on this chapter on multiple choice. So lucky for you guys, but typically they love to ask about the effectiveness of a buffer in 1 or 2 multiple choice questions. Okay, and so just a couple of notes on effectiveness of it. So a buffer is more effective if it has more buffer components. Okay, so let's say we have 2 buffers and they're both a hydrofluoric acid buffer, so HF, with the conjugate base, F minus. Okay, so we're looking at the same buffering system. If we have 0.1 molar of hydrofluoric acid and fluorine, right, that would be a worse buffer than if we had 1 molar hydrofluoric acid and 1 molar F minus, right? If you just have higher amounts of that acid and conjugate It's just going to be a better buffer because it can neutralize more acid or base, right? Buffers, their whole goal is to resist changes in pH, which, oh, I didn't say. I was like, did I even write that? I kind of did. Again, they resist changes in pH. Oh, sorry, I didn't even finish this thought. I must have completely skipped it. I apologize. The buffers will be more effective when the concentration of HB and B minus, it should say, are similar. Okay? They're going to be more effective when the amount of acid in the conjugate have similar concentrations. Okay? With the buffer being most effective when they have the same concentration. Okay, so if our amount of acid and conjugate base, if they have equal amounts, that is when that particular buffer is most effective. Okay, and then lastly, buffering capacity, right? So each buffer can really only buffer like a small pH range, right? After a certain point, it kind of loses its ability to resist either the addition of acid or base. And the reason for it is it just starts to run out of our weak acid or our conjugate base that counteracts the addition. Okay, and so we say that the buffering capacity of any buffer system is equal to the pKa plus or minus 1. Okay, so if the pKa for a particular acid is 5, right, then it would buffer between a pH of 4 and pH of 6 very well. Okay, but outside of that pH range, it really wouldn't be effective at all. Okay, and again, we are just going to go through this problem. It's pretty quick, so I do want to just introduce this to you. However, I was going to say maybe I'll hold out on the challenge problems, but a bunch of them are just kind of in general chapter 14, chapter 15 questions. So I actually do think I'll give you the challenge problems. Okay, but let's first go through this. We have a buffer that contains ammonia, we're given the Kb, and ammonium chloride. Part A, what's the pH? Part B, the volume's 1 liter, we add 0.1 moles of HCl. What's the new pH? Okay, so basically we're adding 0.1 molar HCl, right? 1 liter, 0.1 moles, which is 0.1 molar. So I write my note information at the top, and then I write NH3 aqueous. Again, I always react on the reactant side with water to produce my conjugate acid and hydroxide. Okay, and I write my initial amounts of each of these, right? Because again, we need both portions to have a buffer. And I write my Henderson-Hasselbalch equation, so I have it. Okay, but based on the Henderson-Hasselbalch equation, I know I need my pKa, and I only have a Kb. So I need to solve for the Ka, which would be equal to our Kw, 1.0 times 10 to the negative 14th, divided by the given Kb, 1.8 times 10 to the negative 5th. So once I find my value of Ka, I can take the negative log of it to find my pKa. Now that I have the value of my pKa, I can plug it back in, right? So our pH is equal to pKa, which is 9.26, plus the log of our base, which is 0.25 molar, divided by the concentration of acid, 0.40. When you plug those values in, you'll find that the pH is 9.06. Okay, and how about part B when 0.1 molar of HCl is added? Okay, so realize if we add 0.1 molar of HCl, we're really just adding 0.1 molar H plus. Okay, and so again, my initial concentrations of ammonia and ammonium are going to be exactly like they were before. But now we need to insert some change, right? In which way is equilibrium going to shift? Okay, so just excuse me as I go back a couple slides. Right, so these points here, again, remember, if added acid or base is not an equation, will be plus X. So what does that mean? Or what was I trying to say by that? Well, in this case, we're adding H plus. Now, H plus isn't in this equation, okay? And so I said when acid or base portion that's added is not in the equation, we will be plus X. But what did I mean by plus X? All I meant by that is that the other acid or base portion, which in this case is hydroxide, right? That will be plus X, with X being the amount of H plus we added. Okay, so the change here, I know has to be plus 0.1 to the products and minus 0.1 to the reactants, because I'm adding 0.1 molar H plus, which I'm going to counteract or neutralize with 0.1 molar hydroxide. Okay, so I knew it had to be positive because I wanted equal amount of hydroxides to counteract H plus. Now that I have equilibrium amounts of ammonia and ammonium, I go back and plug them into my Henderson-Hasselbalch equation and find my new pH is 8.74. Okay. Now, just the last slide I want to show before the challenge problems is up here. You'll notice I reacted ammonia with water to make my conjugate and hydroxide. Now, because ammonia and ammonium are both in this, there's a possibility that on your reactant side, you wrote ammonium, okay, instead of ammonia, right? The reason I chose ammonia for my reactant side is in the problem, they gave us a KB, which just made me decide I wanted my ammonia on the reactant side. But if you wanted to write ammonium on the product side, that would also be fine. Okay, and so if we had written ammonium on the reactant side, we would have reacted it with water to produce ammonia and hydronium. Okay, I insert my normal amounts for initial, and then my change, you'll notice I did plus 0.1 on my reactant side and minus 0.1 on my product side. So why did I do this? Okay, now what I'm doing in this part of the problem that I'm showing you is I just added 0.1 molar H plus. Now, H plus and hydronium are the same thing. Okay, and so my change portion here, because I'm adding 0.1 H plus to this system, for the change section, I need to subtract that 0.1 molar from this H plus section, right? Because we're adding H plus and it's in my equation, and so I'm going to subtract that amount from hydronium. Okay, so I subtract it from products, add it to reactants, and just realize here that at equilibrium, my amount of NH4 plus and NH3 are the same as they were if I did it through the other equation. Okay, so however you want to write it, you should get the same answer. Just kind of realize what your sign should be for your change. Okay, and so that'll be where we end tonight. We'll pick up our discussions of buffers next Monday, because Wednesday will be an exam review. Okay, and so here are just some challenge problems. Again, we won't even look at these until next Monday. Okay, so I'll just kind of put it up for about 5 seconds on each slide. But feel free to put any questions in the chat if they arise. Okay, about 5 more seconds on this slide. Okay, I would pay, well, honestly, I'd pay a lot of attention to all of these multiple choice problems. A lot of them do have to do with chapter 14 and are pretty much the same things as were on my exam way back when. But especially ones like number 2, I would definitely take a look at. Okay. Okay, and so here's just kind of the one open-ended. It's kind of just a classic buffer question. Just getting familiar with doing these calculations. Okay, and so I'm going to end the recording here and stop sharing the PowerPoint. If anybody wants me to come back in, I'm happy to do so.